find out is K cap. K cap is going to equal V max over V total. Okay, so we need to know V max. Because here, right, we got 1 mole of pyrophosphate divided by Avogadro's number. Gives you the number of pyrophosphates, right? So 1 pyrophosphate has 6 active sites, and Avogadro's number of active sites is 1 mole of active sites. Right, so let's see if we can find Vmax. Okay. 2,800 units per milligram here, max. 2,800 units per milligram divided by E total, right? So what's the E total in this case? Does he know? Do we know what the enzyme total concentration is? Kilodaltons and convert that into your total enzymes. So what would that buy us? No, that's right. Okay. How else can we approach this? I should have looked at this problem either, so I'm right there with you, right? We know that that is the concentration for K, or that is the equation for K, right? So V max over E total. So we know what V max is, and we know what E total is. In other words, can we get the units to agree, right? So V max 2,800 units per milligram. Let's expand this to say 2,800 times 10 over 15. So 28,000 divided by 15. That's 1867. Right? Everybody see where we got that? Right? 2,800 units per milligram. 2,800 units is 2,800 times 10 micromoles per 15 minutes per milligram. Okay, so this is going to be 10 micromoles per minute per milligram. That's our Vmax, right? Now, E total. What can we say about E total? Concentration is going to equal moles of E per what? Per liter. Right? So let's put that down here. I'm making a mess of this, we'll find out. Mole E per liter. How many moles of E do we have? And can we use that to cancel anything out? Oh. Any ideas? have to do that at some point, right? Because right now we're in micromoles per minute, we're gonna have to do it in seconds. So we are gonna have to do that at some point. This one is the head scratcher. Try to think about what we can do here. Scroll up a little bit. Any ideas? Not an idea among 140 people. All right, well, let's see if we'll work it backwards. All right, so we know the answer is 622. Right, and let's see if we can see what it is that we're supposed to do. 622 equals Emax over E total. We know that Emax is 2,800 units per milligram. Of enzyme. Okay? This E total, we don't know what that is yet. So let's convert this into micromoles per second. Right? So 2,800 or 10 micromoles per 15 minutes comes out to divided by 15, 2/3 micromoles per minute. Divide that by 60. We have 0.011. 0.011 micromole per second. That's what 1 unit is, right? 0.011 micromole per second. Okay, go back over here, plug that in, say V max is 0.011 micromole per second. Let's also assume for now that we just have 1 milligram of enzyme. Right, so we have 1 milligram of enzyme. That means that our Vmax is exactly 2,800 units. So we have 0.011 times 2,800. So I'm sorry, my mistake over here. This will be 31.11 micromoles per second divided by ET. Right? Let's divide that by 622. This means that E total equals 0.05. Okay? 0.05. How did we get to 0.05 molar for E total? Okay? Remember here, we did our conversion over there, we multiplied by 2,800. So for 1 milligram of enzymes, our Vmax is 31.11 micromole per second. Right? So what's happening here? So 0.05 micromole. 0.05 micromole. How did we get there? Okay, so we're assuming all the enzymes being active. All right? It's the same as the number of the active sites, right? We have 0.05 micromoles of active site. If they're all saturated, E total must be 0.05 micromolar, right? So all we had to do was take the answer from our last problem, 0.05 micromoles of active sites. That's the total amount of effective enzyme that we have. We have that many micromoles of active sites that are able to be catalyzing the reaction. So if they're all saturated, we're at E total. So there's our E total for V max, right? So 31.11 micromole per second, which again, we got from converting micromole per minute into micromole per second, multiplying by 2800 because we have 1 milligram, gave us a V max of 31.11 micromole per second. 0.05 micromolar because that's what we calculated the number of micromoles of active sites to be, right? So that's how many we have. Find the ratio, we get 622, the turnover. Right? That's our K2. Alright. So we can do one more homework problem, then I want to move on to some practice problems that have to do with enzyme inhibition.
Could you do number 8 from chapter 1, please?
Number 8 from where?
Chapter 1.
Chapter 1. This one?
Yes.
Okay. You want to go over both parts or just this section?
Just the second part, please.
Okay. All right. So. What do we have? We've got what? I'm actually asking, what do we have for the second part? 100 mils of? No, the second part. Acetic acid?
0.11 buffer, millimolar buffer.
0.1 millimole. Okay, acetic acid. Okay, so 100 mils of 0.1 millimolar acetic acid. pH 5, right? Is this what we have? So, write down our acid dissociation equation. Okay, fine. So we're at 100 mils right now. Okay, we're at 100 mils. Our concentration is 0.1 millimolar. So what's going to happen to the concentration of everything when we dilute this to 1 liter, to 1,000 mils? What's going to say that we had 0.1 millimolar. Let's say that we had 1 molar sodium chloride in 100 mils, and we dilute it to 1,000 mils. What's the new concentration? So you're diluting it by a factor of 10. So exactly, the concentration is decreased by a factor. So we're at 0.1 molar. So the concentrations of everything, right, are going to be diluted by a factor of 10 in this case, going from 100 mils to 1,000 mils. So we're just diluting everything by a factor of 10. But we don't know what we have initially, okay? But let's start with H plus, because that's the easiest, okay? What's our concentration of H plus initially in 100 mils? He's someone who hasn't spoken. This one's a given. What's the concentration of H plus when we start at 100 mils?
1 times 10 to the negative 5.
Yes, 10 to the minus 5, right? Remember, pH is just negative log of H plus, which means that H plus is 10 up to the negative pH. In this case, 10 to the minus 5. What's the concentration going to be when we dilute it to 1,000 mils? 10 to the minus 5 divided by 10, which is 10 to the minus 6, right? So initially, at 1,000 mils, we are at 10 to the minus 6. What about HA and A minus? Well, it's going to be 10 times diluted from wherever it is that we started at 100 mils. So what were the values of A minus and HA at 100 mils? can we figure that out? Alright, don't give me the answer then, but give me how can we figure it out? How can we find what A minus and HA were initially at 100 mils? Which is? Rearrange this to say that A minus over HA equals 10 up to the pH minus pKa, right? So in our case, what does that come out to? I've had so many questions on this one, I happen to know it's 1.77. Right? You can check it on your calculator, check it with my calculator. So check that. And up to the 1.77. There we go. Right? But this is just a ratio. Right? And we have two variables, so again we need a system of equations, we need a way to relate A minus to HA in a different way. So what's another way that we can relate A minus to HA? Yeah, they have to add up to the total concentration of our buffer. A minus plus HA equals 0.1 millimolar. So A minus equals 0.1 millimolar. Let's just call it 10 to the minus 4. Yeah, 10 to the minus 4 molar minus HA. Right? So move that over here. 10 to the minus 4 molar minus HA over HA equals 1.778, which means that HA equals what? .6 times 10 to the minus 5, of course, means that this is going to be 6.4 times 10 to the minus 5. Okay? Now we diluted by 10, so we know that HA then is going to be 2.6 times 10, not to the minus 5 now, but to the minus 6. And A minus is going to be 6.4 times 10 to the minus 6 as well. Right? Now, this is where we're at as soon as we dilute it from 100 mils to 1,000 mils. But now, it's going to reach a new equilibrium determined by the equilibrium constant, or acid dissociation constant rather, of acetic acid. Right? So this is going to go down by some amount, it's going to go up by the same amount, it's going to go up by that same amount. So at equilibrium, we have 3.6 times 10 to the minus 6 minus x. Here we have 10 to the minus 6 plus x. Here we have 6.4 times 10 to the minus 6 plus x. Ka, the pKa for acetic acid is 4.75, which means that the Ka is 10 up to that, negative that, 10 to the negative 4.75. This equals H times A, so it equals 10 to the 6th plus x, 6.4 times 10 to the minus 6 plus x over 3.6 times 10 to the minus 6 minus x, right? So what kind of equation is this? Quadratic, right? So that's a giant pain in the ass. So I'm not going to ask you to do something this complicated on the exam because honestly I was just about to plug it into Wolfram Alpha, okay? Because I don't feel like being asked to solve this equation. But anyway, we solve for x, right? X comes out to be whatever it is. Now we come over here, right? So we know that at equilibrium, the final concentration of H plus will be 10 to the minus 6 plus whatever X happens to be. But what's the problem with saying that? Well, it's a quadratic, so we're gonna have two roots for X, so X could have two solutions. How do we know which one to pick? One of them will always end up being negative, so we'll have a negative concentration of H plus. We know that we can't have a negative concentration, it's not possible. So that's out. So you pick the other one, that gives you your final H plus concentration, take the negative log of that, and that comes out to 5. Right? So whenever we change the state of a weak acid system, right, we always have to consider it's going to reach a new equilibrium. Right? So let's move on here. We've got a couple of more in-depth problems that I put together to show you some real answers. Now, this is not going to be, an all at once. This is going to require some effort on your part. Right? So what I want you to do is pair off with 1 or 2 or 3 people, whoever happens to be nearby, and you can work together. Right? You're going to use your computer, you're going to use Excel or Google Sheets or whatever. Right? So let's start with this one. Simple. And move on to another one section. So finding balances, right? So we have an enzyme called beta-lactamase. Right? Beta-lactamase has this molecular weight, 29.6 kilodaltons. 1 unit or here what we're seeing is basically the amount of, the reaction catalyzed by beta-lactamase is the hydrolysis of penicillin. And this is actually what's expressed in penicillin-resistant bacteria. It takes water with penicillin and it breaks them apart. Right? So penicillin is now no longer effective against the bacteria. In this case, right, we have the concentration of penicillin, the substrate on the left, and we have the velocity of the reaction on the right, right? So the amount in nanomoles hydrolyzed in 1 minute for 50 seconds, right? So what we want to do here is to find the Km value, the Vmax number, and the turnover number, right? See if we can do that. And what we're seeing here is that the amount of penicillin hydrolyzed in 1 minute in a 10 milliliter solution, which contains 1 nanogram of penicillinase or beta-lactamase, is what's shown in this here. So we know that we have 1 nanogram of penicillinase, beta-lactamase. We know that this is in 10 mils of solution. Right? And we know the concentrations of penicillin. Right, so this is going to require a computer, unless you grew up in the 1950s and you used Biochem. What is the Km value, the max number, and this turnover? So it's 3, so I'll give you until 3:05 and I'll check back. Right? I'll walk around. got an answer? For KM at least. Who thinks it's got a KM? Not yet? Alright. Alright. I got
You know how to hack rotates, right? Shoots at us and use it.
Give everybody one more minute and then I'm going to start talking about it. Alright, so, whether you're done or not, let's talk about it. So somebody from this side of the room, been awfully quiet today. Anybody from this side? What is our best guess right now for KF? .25. Why do we say? How did you get to 0.25? You put what into Google Sheets? Okay, so we put 1, 3, 5, 10, 30, 50, and 0.11, 25, all that in the other column. And what did you do after that? Okay, so it looks like what we expected, what we've seen before. Right, it looked like this. So what did you do now? Okay, so it kind of plateaus around, what did you say, 0.61? Okay, and then what? Say that again?
I just found whichever which was half close.
Okay, so let's say we want to be at about what? 0.3-ish, right? And then what concentration does that happen? another way to get us a little bit more accurate answer.
I think all it becomes assuming that we can do like one over S, one over V naught, and then we find your intercepts.
Exactly. Right? So the problem, not that necessarily it's wrong, because the concept is correct, right? But this is just the highest that we know, right? We're at 0.61. And just before we were at 0.58, so we're beginning to plateau, right? But we don't know really how much higher it's gonna go. Obviously, Vmax can't be 0.61 because Vmax is unachievable, always, right? So it can't be that. But is it 0.62? Is it 0.65? Is it 0.7? I don't know. No one, right? At least just looking at the hyperbolic, which is why, right, we want to do a double reciprocal. So how do we do a double reciprocal? We need 1 over V naught, and 1 over S, right? So we do 1 over 1, 1 over 3, 5, 10, 1 over 3, 1 over 5, 1 over 10, and 1 over 30. And the same thing to this, to the right? So we fill this in, and we come up with, of course, is our double reciprocal plot, right? Now all of our data points are going to be real, right? But once we fit a line, we can extrapolate these points here, so we can find our x-intercept and we can find our y-intercept. 1 over V max and 1 over Km. So once we fit a line and we get our y equals mx plus b, right? Well, finding the y-intercept is easy, right? That should be. So now we know our 1 over v max, and we take the reciprocal of that, and we know our v max. Now we can either solve for the x-intercept and find our negative 1 over km, or we can use the slope, right? Because remember, what is the slope of a line we revert by? Km over V max.
Yeah.
Right? So the slope of the line we revert plot, I'm down over here, is Km over V max. So if we know the slope, M, this equals Km over V max. We've just solved for V max. We got it from B, the y-intercept. So now we can multiply the slope by that V max, and there's our Km. Right? And now we have more hard values. Right? So who was able to get through all of that on Excel or sheets or whatever? What are the actual values? Did anyone try to do this way? Raise your hand if you tried to do it this way. Raise your hand if you tried to do it the first way. All right. So when we're calculating Km and Vmax values, it's dangerous to rely on kind of estimating here. We don't know how much higher this is going to go. We don't know what the limit is. We don't know what the Vmax is that we're going to fit, right? So the best way really to calculate these is to plot them as double reciprocals. Now, I'll post these up to class because there's one about enzyme inhibition that we're not going to get to. It will take too long. All right, so let's look at here, okay? So catalysis is between the peptide bond and the small peptides is shown in the table, okay? And that little down arrow just shows where it's being cleaved, right? So the first is being cleaved between an A and a glycine, the second one after an A and an alanine, and then the third one after, or between an A and a phenylalanine, all right? So now, the question is, we take equimolar amounts of all three of these small peptides, and we put them together in a beaker, and we add our proteins, which is going to cleave all of these. Which one is going to be cleaved or digested the quickest? Which one is going to be digested the quickest? So how do we start this problem? What's the characteristic that we have to find? But really, what is it that we're trying to determine? If what we're trying to see is which one's going to be digested the quickest, what is it that we're trying to determine? phrase it a different way. What if we're trying to figure out, essentially, what it is which of these tripeptides is going to be recognized the best by the protease? How do we figure out which of these peptides is going to be recognized the best by our hypothetical protease here?
K-cat over Kn.
Yes, K-cat over Km. What do we call K-cat over Km? What is that called?
The
The specificity constant, right? Remember, we go back over here. What is K-cat over Km? Yeah, right? So if we say we have our V naught equals K cat times ES, right? And we also know that Km, the Cayless constant, is equal to, of course, K minus 1 plus K2 over K1. But remember, from the derivation, it's also equal to E times S over ES, which means that ES is equal to E times S over Km, right? It's just a rearrangement here. So we can plug in this ES over here and say that V naught equals K cat ES, or no, sorry, K cat times E times S over Km. In other words, K cat over Km times E times S. So now what do we have? We have a velocity, we have concentration, and some constant here. This becomes some rate constant. It doesn't have a name, and it's not real, right? But it becomes some rate constant for the interaction between E and S, right? The higher the rate constant now at any given concentration of E and S, right? So let's say that we're holding them equal, right? The higher the rate constant, the higher the velocity, so the better the interaction between E and S. So K cat over Km is literally how well do E and S bind, right? So that's the question that we're trying to answer over here. Okay? Well, how do we find this out? Well, we have K cat, we have Km, right? So you see 24 over 4 was at 6. 30 divided by 1.5 is 22 and a half. Oh no, 20, you're right. 18 divided by 0.5 is 36, right? So we have what? We've got 6, 20, and 36. So which one binds best? The first, second, or third? The third one, right? It's got the higher K cat over Km value, 36. That means that it's got a higher interaction between depths, right? Which one binds the worst then, right? Which is going to be digested the slowest? Well, that would be the first one, right? Rate constant of 6, K cat over Km is 6. Okay? Now we repeat, let's say that we repeat this here with this peptide ENTIF, okay? And observe that we get a Km of 9 millimolar and a K cat of 18 over seconds, right? So what feature of the amino acid sequence is likely to be recognized, right? So let's see here. Remember we have 6, 20, and 36, and now what do we have? We have 18 over 9, which is 2, right? So is that a good value? No, right? It's not very high. And we've seen as high as 36, and then 20, and then 6, and then now 2, right? So what is the characteristic? What do they have in common, right? What differentiates, let's say, number 1, which is 6, and the new one, which is 2, right? So those two are separated. And number 2 and number 3, right, which are 20 and 36, so those bind much better. What do those two have in common compared to the new one and peptide number 1? What do you think? Well, that's just the sequence of the peptide, right? So it's EMTA and then either G, A, or F. The new one is EMTI and then F, right? So let's compare the most similar one then, number 3 up there, right? So the only difference is that we have an A versus an F. But that one's got 36 K category K in, and this has got 2. So what's the only difference? That that alanine versus I, right? So what's the difference between those two then? A versus I. Is one polar and one non-polar? Are they both polar? Are they both non-polar? No, not the, well, the KMs are different, yeah. But of the substrate, right, what's the similarity and differences between, right now we're comparing EMTAF, that substrate, so that string of amino acids, versus EMTIF, that string of amino acids. These are going to be acted on by our protease, okay? So what do they have different? EMTAF versus EMTIF.
The resolution in the ETAF is positively charged. But
The what?
Alanine and isoleucine are both non-polar, but
They're-
isoleucine is bigger.
Right, they're both non-polar, but isoleucine is bigger, right? So we have a big non-polar residue followed by another big non-polar residue, phenylalanine. Well, that seems to be very bad for this protease, right? So we have a big non-polar next to a big polar. That's bad. Whereas if we have a small polar next to a big polar, that seems to be very good, right? Let's see if the pattern continues. Well, we have EMTAA, right? Well, that's not as good. But that makes sense because we have a small non-polar next to a small non-polar. So it's not as good as having a small non-polar big to a big non-polar. And the first one, EMTAG, right? Now we have a small non-polar next to an even smaller non-polar, right? So what is this enzyme recognizing? It's recognizing just a small non-polar residue in a peptide bond with a bigger non-polar residue, right? And this is how these enzymes are characterized, right? We look at what it is that they interact with and see what do they have different compared to things that they don't interact well with, right? Can we find some kind of pattern, right? Now we test that pattern. That's how it was discovered that trypsin cuts specifically after lysine and arginine residues, whereas thrombin cuts only after arginine residues, right? So I'm looking for these patterns. Now there's one other practice problem. Here, this is a pretty simple practice problem. Take a look at this. There is one that I do want you to try, right? This is related to the first one that we did. And it involves both finding Km and Vmax values, but also looking at inhibition, right? Seeing what type of inhibition this is, what's the dissociation constant between the enzyme and its inhibitor, right? And seeing how these look in real life.